So our third speaker in this session is Dr. Grace Gu, and she is from the Additive Manufacturing in AI and UC Berkeley. So she's a professor at UC Berkeley, teaches a class on what happens to a material when it feels stress. Her research is on 3D printing and bio-inspired materials. And in her free time, she loves traveling and playing tennis. I love those also. Welcome. We're so glad to have you here, Dr. Grace Gu. Come on up.
Hi, everyone, and thank you so much for the very nice introduction. And I want to say how inspiring the last talk was, Dr. Hallinson. I hope to meet you one day. It was really inspiring to learn about your career path and how you got to where you are today. And I'd love to talk to you more about bio-inspired materials. That's something I'm really passionate about. I won't be talking about that today, but actually I'm talking about AI. So perhaps we have stuff to talk about in the future. So yeah, thank you so much. And really good to meet everyone virtually. Hope everyone is staying safe during this pandemic. And I'm excited to share with you today my research on sort of the merging of additive manufacturing and artificial intelligence. And let me see if I can close this real quick. And I want to first start off with discussing a little bit about material selection methods. So how do we usually select materials for various applications? Applications could be like designing a cell phone screen, could be designing your laptop screen, to designing a cup. So how do we usually pick materials for these different applications? Well, one method is using what's called an Ashby chart. So an Ashby chart is shown here, where you have material properties of interest. Here is strength. So basically, how strong is this material? And here on the x-axis is density. So basically, how heavy is this material? How light or heavy is this material? And then you take materials that satisfy these properties and you populate this chart. So you can see materials like ceramics and polymers. You also see aluminum. So you see all these materials that satisfy these properties. And so let's just say you're designing something and you're looking for a material that is light and also very strong. Now, using this method, so basically, going sort of like pinpointing this material using this kind of Ashby chart, it may point you to the direction of aluminum. So aluminum is typically a pretty strong material and a pretty light material. And so using this method, it's quite nice because it gets you an answer. It tells you, try out aluminum. But this kind of like method to look for materials or to select materials for various applications has a couple of challenges. So one challenge is that the material that we're looking for does not exist on this chart. So let's just say, we're looking for material that is in these white spaces, right? So these are empty spaces. We would like a material that is very strong and very light, right? So in this potentially in this corner here, but it's pretty empty. So if we use this method to select materials, and we're looking for material that does not exist on this chart, we're kind of out of luck. So that's one challenge. And the second challenge is that the material that we're looking for does exist. So, we found the material that we were looking for, but it's either very expensive or it's very difficult to manufacture. So there's challenges to actually manufacture it. So in my group, at Berkeley, we're really interested in a platform that overcomes these two challenges to design and manufacture materials with specific functions and desired properties. So applications could include medical implants, can include protective armor, where all these applications have very specific requirements. We're looking for very specific things from these types of materials. And what is unique about our methods is that it can propose many options that correspond to our material property needs. And what's possible is that we can screen through these options and see which one's potentially more cost effective or maybe even easier to manufacture in bulk. And so here are a couple of examples. These are example projects in my group that we're really interested in and also our research interests. And one of our big interests and our current research projects all sort of like merge is that they're at the intersection of additive manufacturing and artificial intelligence. And so, probably a lot of you have potentially used a 3D printer in the past, and And what's really exciting about additive manufacturing or 3D printing is that we're now capable of printing or fabricating designs that were previously impossible. And what I have here in these blue circles are all the benefits that 3D printing offer us. We're talking about on-demand fabrication, less waste, right? Because it's an additive method, potentially sort of like lower cost and rapid prototyping. So these are all the benefits that additive manufacturing offers us. However, there's some challenges with additive manufacturing or 3D printing. The parts that we print are not always perfect. So perhaps some of you have printed with a fused deposition modeling printer or FDM printer. And sometimes when you print, the part that comes out sometimes has defects, right? So it doesn't come out perfectly. So these defects can occur. And the thing is that what we have realized in literature is that what dominates these defects is how you choose your process parameters. So all those printing parameters like printing speed, printing speed, like power input, flow rate that's coming out of your nozzle. All these parameters dictate how well it prints. And so currently, the way we sort of correct for defects during printing is through trial and error. So we're just changing these process parameters in real time. So we're going to increase velocity by 1, or we're going to increase flow rate by 1. So we're going to basically change these in real time. However, this can be very inefficient, right? And so is there a way we can do this automatically? Because if we actually want to 3D print in harsh environments, so we're talking about harsh environments like, let's just say space, in environments that are constantly changing temperatures, like in the morning, it's a certain degrees, and then it's like at night, it's completely different temperature, or changing pressure. What if we want to print underwater? So, all these kind of environments, we really need to make sure that we can monitor, ideally by itself, right? Because we're not going to be able to have an operator in very harsh environments. And so can we develop these like autonomous 3D printer systems that can monitor for defects and correct for defects in real time? And that's exactly what we're interested in my group, sort of combining AI to help us do this. And so in order to correct for defects, we need to detect for them. And so what we have done is created this system and we have created this 3D printing system, then added these sensor technologies and specifically cameras. So these cameras are going to capture images in real time. So you're printing and you're capturing these images, and you're going to capture this image and you're going to send it into a machine learning framework. That our machine learning framework is then going to be able to categorize these defects. And then it's going to correct for these defects by changing these process parameters. So I'll show you examples of defects in the next slides though. So these are the different process parameters we can change. These are just examples: printing speed, flow rate, nozzle height. And so we're going to change these in real time to correct for defects. And so what do I mean by these defects? Well, these defects, these are some examples. So this is a good quality part that's printed. And these are the two sides here are sort of the defected or imperfection, imperfection-based parts, where here in this case, these are under extruded and over extruded parts. Under extrusion, what that means is that not enough material is coming from your nozzle. And so that's why you see all these pores, right? So all these like undesired pores in your material. And typically these pores, they weaken your material. And so that's undesirable. And here is the over extrusion part. Basically, too much material is coming out of your nozzle. And so that's why you see these like unsmooth areas here. And so ideally, you want a part that doesn't suffer from either of these imperfections. And so I'll show you sort of in general. So what we want to do is detect for these imperfections and then correct for them sort of on the fly. And so this is an example of how our platform using AI works. So we have here a part. So this is a single part. And you see in the beginning, you see these pores. And so in the beginning, we have this imperfection of under extrusion. And so our system, our AI system is telling us a probability. So basically it's telling you the probability we have a defect. All right, so it's not going to just tell us we have a defect. It's going to tell us what's the probability of having one. And so here it's telling us we have a 70% probability or chance to have a defect. And that's actually true if we actually look at this part. And then we're going to correct for those process parameters in real time. And you can see this probability starts to decrease of an imperfection. And then a good quality part, which is shown here in green, starts to increase in probability. And so you can actually see this stark transition from an imperfected part to a good quality part. And this is, again, this is one single part that's printed. And I'll show you sort of what our interface looks like, sort of this, what we call a smart AI system, where you have, this is the printing, this is a printing, real-time printing process. And these are our images, our AI images that we send into our algorithm. And it's going to tell us the probability that there's a defect. So it's telling us in the beginning, you have a high chance that you have under extrusion, right? And then this under extrusion probability starts to decrease. And it starts to decrease because we're going to change this flow rate parameter, right? So correcting for these process parameters really helps us to make a better part. And so then you see a probability of a good quality part, which is shown here in green, starts to increase once you change your flow rate. And so it really shows that our system, our platform is capable of detecting for defects or imperfections and self-correcting in real time. And so, so this is our previous work on our system that tells us, hey, you have a defect, you need to do something, right? So, but something we're really interested in is, I don't want our system just to tell us that we have a defect. I want our system to tell us where exactly our defect is. And what's useful about that information is that it can tell us the evolution of defects. So our understanding, so the science behind how these defects start to form in 3D printed parts. And so this is sort of what we call a global defect detection system. It tells you, hey, you have a high chance of a defect. And so recently we've been working on this local defect detection platform. And this local defect detection platform, the aim of it is to tell us local information, to tell us where exactly is your defect. And so this problem is actually pretty difficult because you can see that when you're printing, you have so many things at play. So you have your background. So you have your background, like you have your nozzle. When you capture an image, you have so many things that's happening. You have your background, which includes your nozzle. You have parts that potentially are good. So this is the green area here. You have a part that's defected. So this is telling you this is the yellow here. And then you have not only that, but you have your previous layer, right? You have you're actually printing on top of a previous layer. So you want your algorithm to sort of eliminate that area, right? So sort of in our machine learning algorithms, we're masking and sort of categorizing all these different areas. And you can see that these are sort of the ground truth. And this is sort of the real data telling us where are all these components. And these are the predicted from our machine learning algorithms. And you can see that it's actually able to predict correctly these colors pretty well. And so this is sort of our interface sort of happening in real time and monitoring these local defects. And so what's nice about the system is that it creates for you this profile of exactly what's happening. So here in the green, is telling you this is a good quality part. And here in the yellow is telling you this is over extrusion. So this is a defective part. So we can actually plan out this image that tells you exactly what's a good part, what's a good area, and what's a defected area. And we can learn a lot about these evolution of defects this way. And so this is sort of these in-plane issues that can occur when you're 3D printing, but there's also out-of-plane issues as well. And so these out-of-plane issues, an example was like delamination, right? So your layers are not sticking that well together. And so in order to detect for delamination, we have installed cameras sort of on the side. So basically your cameras cannot just look at one location. It needs to be installed in many different locations because defects can occur in many different areas. And this is something that we have learned and something that we have to implement for our overall defect detection system. And so these are examples of delamination issues. So, and delamination is dictated by something called nozzle height. So basically, how far is your nozzle from the print bed? And you can see here that if your nozzle is very high, and you can think about it intuitively, if you're printing from too high, then your layers are not going to be stuck to each other very well. So you can see this delamination here. However, if your nozzle is too close to your print bed, your layers are going to be squished together, which is also undesirable. So these are all things that we need to categorize using our machine learning platform. And so these are using like traditional printers with like traditional engineering materials. Recently, we've been also looking into bioprinting, so printing these materials that can be used for the biomedical field. And specifically, these are hydrogel-based materials. So we're looking into applying our platform into these bioprinters as well. And very recently, we've also been looking to metal 3D printing. So what I talked about previously, just all these polymers. but we're also looking into metal 3D printers systems as well. Metal 3D printing is often dictated by this issue of residual stress. And it turns out the process parameter that really dictates residual stress is actually how the printing pattern that you're printing in. And so we're looking into the effects of printing pattern and these residual stresses. And this involves creating these really high fidelity simulations to help us train our models. And we have written a review paper on the topic of machine learning for advanced additive manufacturing. And if you have time, we'd love for you to check out our paper. And I want to end with my last slide. I know we're really short on time, on sort of the vision that I have for these design and manufacturing platforms. So if one day we want to go to Mars, we won't be able to bring all the things that we need. So examples include, we won't be able to bring all the chairs that we need, all the tables, all the windows, all the infrastructure that we need. It would be very heavy, right? So therefore, it's going to be really important to be able to, in the future, design and manufacture in Mars. And in Mars is just an example, but it could just be in challenging environments where you're not going to be able to, bring all the things that we need. And so developing these platforms will be really critical in the future. And so hopefully, with all the work that we're doing in the research community, and in addition to other groups in this field, we can get a little bit closer to this vision. And so I will stop my talk here, and thank you so much for your attention.